Chapter 13 is all about this topic known as electromagnetic induction. Some of the concepts, especially starting out, are going to feel a little familiar because we've done some stuff already that's kind of like this. And then very quickly is going to turn a little bit magical and a little bit complicated. Okay, so bear with me today because we're going to do some of this a little bit slowly. So first of all, before we can introduce at all the idea of electromagnetic induction, we have to talk about another type of flux. And since we already learned about electric flux, I think this concept should come rather quickly because the idea is exactly the same. You can see it described there as the amount of magnetic field that's passing through a given area. So you might even expect that the equation is going to look extremely similar as well, except this time we're going to put B as a subscript for the magnetic field, and it's going to be the dot product of the magnetic field vector and the area vector. So instead of E dot A, we've got B dot A. All right, so of course that's going to be the magnitude of B times the magnitude of A times the cosine of the angle between those two. Except for substituting in B, this works exactly like electric flux. So do you feel okay about electric flux? So therefore you feel okay about magnetic flux, right? I don't know what that was. Okay? So we see here at the bottom, magnetic field. They're looking at a particular area. The good thing about magnetic flux is that immediately it's more physical. So you can see that instead of just some arbitrary space in the air, they're looking at a physical loop of wire. So just imagine a circle of wire and how much a magnetic field is passing through there. So immediately our area becomes a physical area, an actual thing that's making up that area in space. All right? So what are we going to do with magnetic flux? It turns out that if magnetic flux through some area is changing, and specifically if the magnetic flux is changing through an area that's made by a conductor, like a wire, well then in that wire we can produce a current. If the magnetic flux through a given area of wire is changing, then a current gets produced in that, even if it's not connected to a battery or a voltage source or anything. So if you just take a look on that previous slide once again, notice that loop of wire? It's just a loop of wire. Just there it is. It's connected to nothing. It's just hanging out in space all by itself. We can make electrons move around that loop of wire if I change the amount of magnetic flux that's passing through it. And you'll see this little point below, and I hope this should make a little bit of sense based on things that we both have talked about, and at least us haven't talked about yet, but theoretically have been talked about in some video or lecture notes or substitute teacher. Okay, so somewhere in there, these concepts have been discussed. So let's see. I do remember that, how many days ago? 10 days ago or something, we discussed that currents produce magnetic fields. So if I have charges that are moving, and specifically if I have a bunch of charges that are moving on a wire, there's a magnetic field that's created around that, and we did the whole right-hand rule thing that dealt with that. You vaguely are okay with that? Yes? Maybe? Somebody nod. Please help me out. Yeah? Okay. What we didn't personally between us talk about is that magnetic fields cause a force on charges that are moving. And there's another right-hand rule for that, and another equation, and all of that stuff, okay? Just keep in mind that this is all about change and motion. So if the charge is just sitting still, it doesn't create a magnetic field. If it starts moving, it does. If a charge is just sitting in a magnetic field, it doesn't feel a force. But if it starts moving, it does. Okay? There has to be some sort of motion or some sort of change that's going on. So I can kind of, if you just sort of theoretically think about these two concepts just a little bit, the idea that if there's a magnetic field there, it will cause a force on charges that are moving, step back from that just a little bit and imagine maybe a charge just sitting there, and now I do something with the magnetic field. I change it. I create a changing flux. You can almost sort of sideways wrap your brain around imagining that magnetic field could push the charge just by means of it changing in some way. Okay? So this is sort of building on those last two chapters and sort of bringing the whole concept together. Now, if this happens, if this phenomenon happens, don't think of these two terms as anything special. We just give them a particular name to denote that they came from the idea of induction, from changing magnetic flux. So if there is a current that's produced in this magical way in a current loop, we call it an induced current. It's no different than a regular current. It's still moving charges. You can use all the same equations as for current. It's just produced by induction. And of course, I can't have a current unless there's a potential difference somewhere. Remember, the charges have to have a place to go and a reason to go there. The reason to go is a voltage, and if this is happening through induction, we call that particular potential difference an induced voltage, okay? Just specific names for currents and voltages produced in this way. Your question first. We're getting there. Sort of getting there. Next two slides will pull it all together. Back here? Same thing? Okay. So induction. What is induction? Induction, broadly speaking, is when we get a current in sort of a magical way, not produced by like a battery or a power source of some type, but instead simply produced because magnetic flux is changing in some region, all right? We can see this process below. The process below is describing one way we could get current to be induced in some wire. So take a quick look at what we have here. Notice this little apparatus. Nothing special. At the top, we have a meter that will allow us to detect current. You can see in this particular case, like the needle is over to the right to indicate some positive current is currently happening. Underneath that, there is a bunch of little loops of wire that go around in several circles and just connect to this again. There's no battery, there's no voltage source, there's no capacitor, there's no anything. It's just loops of wire and something to detect current. Currently, yeah, I know. Terrible. Oh, I've missed this, haven't you? Yeah, no. So currently there's a current because of what's happening over here. Notice we have a bar magnet. The north end of this bar magnet, the magnetic field points out of the north end and wraps around to the south end. And there's an arrow here to denote that this magnet is currently moving with some velocity in this direction. Okay? If it's moving with some velocity in this direction, you might imagine that more and more of these magnetic field lines are passing through the area defined by these multiple current loops. Okay? As it gets closer, you can imagine more and more magnetic field is passing through the loops, which means that the magnetic flux is increasing. There's more and more magnetic flux as this bar magnet gets closer. That's a changing magnetic flux, which results in a current moving around this loop of wire and through that meter. Okay? If I stop it, so all of a sudden just bring it to rest, notice this needle goes to zero, there's no current. If I do exactly the opposite, notice they've got an arrow here saying, ooh, let's make the magnet leave, which means whatever magnetic field is passing through here is now sort of departing, it's decreasing. We get the opposite effect of a negative current, a current that's passing in the opposite direction. We're going to quantify this on the next slide. Yes, ma'am. No. Changing magnetic flux makes charges move. So when we're in this particular arrangement, there are electrons everywhere in here just sort of hanging out, but the amount of flux isn't changing. It's just a constant because the magnet itself isn't moving. If I move the magnet, the charges that are in this coil move to correspond to that. Okay? Changing magnetic flux produces a current. Are we okay so far? Like just broadly understanding the concept? Okay? So the whole thing that defines exactly how much current and voltage and all of this stuff that you get is known as Faraday's law of induction. Faraday's law of induction. And we've got a lot of space here to write an equation that's not terribly long. So let's see. For this thing that we call the induced voltage, typically this symbol is used, which is, I guess, kind of an epsilon, but kind of not in another way. This is the amount of induced voltage, and it's equal to negative capital N times the rate of change of magnetic flux. The amount of induced voltage that's created in the disconnected circuit is equal to negative N times the rate of change of magnetic flux. This big N is just simply the number of loops. The number of loops. Nothing too complicated there. And of course, the magnetic flux, we can use the equation from what we had before. So we could rewrite this one more time and say this is that. And then here we're going to have be a cosine theta over delta t. All right? Questions once again? In the back. Yes? Yes. Essentially, it is an EMF. It's measured in volts. It's a voltage. There we go. Anybody else? Yes. Why is there a negative sign? That's a good question. Change slides. That's good. Thank you. He's like, keep moving. What about the negative sign? All right. So if we're just worried about how much voltage, you're not going to think about that negative sign at all. Instead, you'll just use the magnitude, and it'll give you some amount of voltage, some positive voltage. The negative sign is a law all to itself, which I think is kind of unique and weird. I wish someone would take a negative sign in an equation and give it my name. That'd be kind of nice, right? It's like, there's a negative sign in there. Let's call that the Lohorn negative sign. But alas, no, it doesn't happen. Instead, Mr. Lenz's law gets credit for what the negative sign means. Don't you kind of love that? It's amazing. So, what is Lenz's law, and what does the negative sign altogether mean? It says this. It says that the induced current and potential difference or voltage, and I'm going to add to this that there's one other induction that happens, which is magnetic field. The induced current, voltage, and magnetic field, we'll say, are in a direction that opposes the change in magnetic flux. Everything that gets magically created or induced in this disconnected circuit happens in a direction that's opposing anything that's changing. So magnetic flux changing is what's making it happen, but the direction in which it happens is in a direction that opposes that change. And we're going to use a similar diagram as from the previous slide to kind of describe what's meant by all of that, all right? Is everyone done writing before we start talking about these diagrams? Because they always confuse people the first couple of times we do it. In fact, the next 10 slides or something is primarily about Lenz's law because it gets so confusing for people, all right? So take a quick look at what's happening here on the bottom left, okay? All of these fields and things that are happening here, if this magnet is not moving, all of these fields don't exist. There's just a loop of wire there. There's no current. There's no current making a magnetic field. Nothing is happening. It's literally just a loop of wire. All of this happens in response to this magnet having a velocity coming closer to the loop. If it stops, everything dies. It's all gone, okay? So let's take a look at what's happening. If this magnet is coming closer with its magnetic field that's pointing to the right, you can imagine that this loop is experiencing a change from nothing to having a magnetic field pointing to the right, sort of being forced inside the loop, okay? It doesn't like that change. In fact, as this bar magnet gets closer, it's experiencing a stronger and stronger and stronger magnetic field passing through the center of it. Let's write down magnetic flux once again. You could think of this as B is getting larger as the magnet gets closer. Can you agree with that? Maybe? If I take the magnet away, make it go the other way, well then B would be decreasing inside the loop. Okay? So we'll say that B is getting larger through the loop as the magnet gets closer. Okay? The loop says no thank you. And it's going to do whatever it can to try to oppose this happening. So in other words, if there's a magnetic field that's pointing to the right, getting stronger, it's going to create its own magnetic field to the left in an effort to cancel it out. Okay? It started with no magnetic field passing through it, and it's going to try to keep it that way. So all of a sudden, stronger magnetic field this way is growing as the magnet gets closer. So the loop itself has a magnetic field that's induced within it that points the opposite direction, trying to cancel out that growing magnetic field. Do you follow that first of all? Okay? Once we have that, we could say that, through the middle of the loop, we have a magnetic field vector that points this way, which is induced. That's not the magnetic field vector that's coming from the magnet itself. This is a magnetic field vector that's being produced by the loop. From there, we can use the right-hand rule to determine which direction current must be flowing around the loop, right? So I can take my thumb and point it in the direction of the magnetic field through the middle of the loop, and you can see my fingers wrap around this way, which is the same way they've drawn the current there. It sort of goes away from you at the top of the loop and goes like this. Okay? Yeah. Yes? It's a good question. Magic. Yeah, not really. It's loosely connected to this concept right here. It's that this time, instead of having a charge that was already moving and a magnetic field that's constant, I'm kind of doing the backwards thing. The charge isn't moving, but the magnetic field is changing in some way. And that change in magnetic field makes the charges in the loop move. You don't need to know quantitatively how that process is happening, but you do need to be able to use the process as we describe it here. Okay? Yeah.
Where is theta measured from in the flux equation?
Where is theta measured from? That's the angle between the area vector, which is perpendicular to the loop. So maybe if you drew a little area vector this way, and the magnetic field vector, which started in the same direction. So the angle there is 0. Okay? Let me get rid of those lest they confuse. Yes? Why is what pointing? This is just one of like 3 or 4 different right-hand rules that we can use. Yeah. So if we're talking about a connection between current in a loop and the magnetic field directly in the center of the loop, you can use your thumb in the direction of the magnetic field and the direction your fingers curve tell you the direction of the current in that loop. Okay? Yeah. Doesn't really matter as long as you're looking at magnitude. Just the fact that it's 0 or 180 means it doesn't change the value. Yeah. It does matter because we're looking at this rate of change here. So the amount of time it takes for the flux to change a certain amount does affect how much potential you get. So when I'm trying to figure out the direction of the current that's induced, well, none of that matters, but the strength of that current will be related to how fast I move the magnet. Okay? So if I look at the opposite case, let's make sure this makes sense. Notice, we've got the magnet here that's moving away. As it gets farther and farther away, that means that the magnetic field from it that's passing through the loop is decreasing. If I moved it infinitely away, there'd be no magnetic field passing through the loop, right? So as it gets farther away, we could go back to this equation and say, B here is dropping, which means magnetic flux is dropping. However, that magnetic flux is because of a magnetic field that's pointing to the right, okay? So you might imagine that the loop is sitting there sort of enjoying the magnetic flux, if you want to think about it that way. I don't know. Can a loop of wire enjoy anything? Let's just imagine it can, okay? So here, I'm the loop of wire, and it's like, magnetic flux is passing through me. That's nice. And then all of a sudden, the magnet starts to leave, and I'm like, who turned off the magnetic flux shower, I guess, if you want to think about it that way? Someone's turning it down. I don't care for that, right? So if I have magnetic field that's passing this way through me, I want to keep it. I'm going to oppose the fact that something's taking it away. So that means this time I'm going to induce a magnetic field in the same direction as what was already there in an effort to maintain the status quo. It's not about being zero or not zero. I just want to keep what's there. So I already have magnetic flux to the right. I'd like to keep it there, so I'm going to create my own magnetic field in that direction in an effort to maintain what's there. If that happens, well, notice once again, now we've got B induced this way, and now we've got a induced current that's coming around this direction. Okay? Yeah? The distance of what? It all matters based on that equation. So the speed matters, like what field I started with and what it changed to. All of that's coming into play in the calculation. Yeah.
So when the magnetic bar is not moving, it's considered at the optimal distance?
When the magnet isn't moving, simply nothing's happening.
So there's no opposition?
There's no opposition because there's nothing to oppose. There's zero flux. Well, there could be flux, but there's zero changing flux. Okay? I want to write on top of this that both of these currents that are drawn here, these are induced currents. So we'll write those as I-N-D. Okay? Induced currents. And we're going to just take a breath here for a second and make sure everybody's all right. Yes. What's that? How are we measuring it? We're not really measuring it so much as you're going to have to do a calculation. It says it has battery, but it's not turned. Wait a minute. I think I hear it again. Yeah, it's there, but it says it's not connected. It's supposed to turn green, but whatever. We'll be fine, I think. Look, everything is just coming apart now. All right, who else has questions? Yes. The original state, as in... Yes.
But before the magnet acted on it, there's originally a magnetic field.
So if the magnet is just, say, sitting there nearby, right? If it's just nearby, then it is experiencing whatever flux this is producing. That's passing through it. There's an amount of flux, but there's not a changing flux. So that would be the only magnetic flux that's there. It's only when I start moving it and I'm changing how much is there, then all of those other blue lines get produced. Up and down. So you want to move it this way. Same thing, but a lesser effect, because I wouldn't be changing how much flux is there as rapidly because of the direction of motion. But you'd still get some induced current. Yes. Yeah. So if I could measure like whatever magnetic field is being created by this bar magnet at this point, and then also measure this area, that B times A would tell me how much magnetic flux I'm starting with. And then as I move the magnet closer, B would be increasing, so the magnetic flux would be increasing. Yeah.
Does the locality of the magnet matter where it is?
That's anything. Ooh, see? It's got a little life left in it, but it's going to be in and out, people watching the video. I'm sorry. So in this particular case, magnetic field created by something. So there's a magnetic field that's passing through the loop of area A. There's a magnetic flux. Now, if you just imagine maybe, I don't know, somebody somewhere has a big dial. It's like a magnetic field dial, right? And they can go and turn the thing down, okay? That's what's happening from the left picture to the right picture. So someone turned down the magnetic field. And you can see that reflected because the number of lines that are being drawn there, there's fewer of them, right? There's less of a density of lines. We know that that indicates there's less magnetic field in that region. Well, the loop doesn't like the decrease, right? So it says, I would very much like things to be like this again, like we had on the left. And I kind of like the way they did this diagram because they draw additional magnetic field lines to indicate that it's like trying to replace what was lost. So these magnetic field lines, ooh, that one and that one and that one, these are induced by the loop in an effort to recreate what we had on the left, okay? A magnetic field passing through the loop to the left is induced in an effort to recreate what was lost. And once again, we can point our thumb in the direction in the middle of the loop of that induced magnetic field, and your fingers give you the direction of the induced current around that loop, okay? If anything just stops, if all of a sudden I stop turning down the magnetic field, that current stops, the induced magnetic field stops, everything stops, okay? And it's just going to live with itself as it is. It's just going to be a loop of wire once again. So let's see. B induced, that's all of these little pinkish sort of lines, and we'll say that this current here, that is I induced, okay? So we could take this one step further, right? If we have this equation, BA cosine theta, this is the only one that we've looked at as the possibility of changing the magnetic flux. If anything else in there changes, that's a change in magnetic flux as well. But all the same rules with Lenz's law and everything still applies. It's going to try to oppose the change. So if there is a way for me to change the area, well, that would apply too, but it's a little difficult to carry out. That's like I've got a loop of wire, and all of a sudden it just magically gets bigger. I'm not real sure how that's going to happen. So that seems a little bit strange. A better way to maybe deal with that is to think about A cosine theta. If I were to tilt the loop of wire, we once again have a case where there's like less space for the field lines to get through. If I tilt it all the way to the side, none can get through. Okay, so that's a way to sort of decrease the effective area, is through a rotating loop. So what I'd like to do is talk through a bunch of examples with this, not starting with this one because it's terribly drawn. Okay, so we're going to skip that one and instead look at something like this. There's a green loop of wire in a magnetic field that points into the screen. So these little X's indicate the magnetic field that's already there. And the loop is being dragged to the right somehow. First of all, is the magnetic flux changing? Is there any difference in magnetic flux, say, when the loop is there versus when the loop is, I don't know, like right here, and is the exact same size? Same area, same strength of magnetic field, same direction of magnetic field, same everything, right? So there is no change in flux. We could say that delta magnetic flux is equal to 0. There's no change. And if that happens, there is no induced current. This loop of wire just moves through the magnetic field and nothing happens. Okay? So what if we change that a little bit and now say, it's leaving this region where there's a magnetic field? Talk to your neighbors about this. What is the direction of the induced current in the loop? That's a lot of discussion. That's good. That means there's a lot of confusion. That's bad. Who says number 1? 2? 3? It looks like we're leaning toward the correct answer a little bit. It is losing magnetic flux that's into the screen. So it's going to do what? Essentially this. It's like, no, they're going away. I will try to add my own magnetic field in that direction, which means that B induced is into the screen as well. Once we have that, well, it's like point my thumb in the direction of B induced, and that gives me the direction of the induced current, which is clockwise. Okay? So clockwise for the induced current there. Can I draw that? I don't know if I can. So let's see. Let's do this. We'll say thumb in this direction. Fingers in direction of I induced. So that means that there's going to be a current going around this direction. Okay? What happens once it completely leaves the magnetic field and just keeps moving? Would it? Eventually it's going to stop. As long as there's still a decrease in how much flux is passing through, then there's still going to be a clockwise current. As soon as I get to a point where there's no magnetic field passing through, and if it keeps moving, there's still no magnetic field passing through, that's not a change, so there would be no current. Okay? Let's do another one. I don't know what's up with this. Direction of the, what is happening up here? Yeah, that is definitely an F. I would agree with that. Why does it exist in that location? I have no idea. Let's make it go away. You sure? Are you? Locking it in, huh? Oh, that's serious. Phone a friend? Does anybody need to phone a friend? I wish we had money to just do that with. So let's see. What is the direction of the induced magnetic field? First of all, it's going to be going out of the screen. What is there is growing. It's increasing, and it doesn't like that, so it tries to cancel it by creating a magnetic field in the opposite direction. So B induced is out, and we can use that symbol to denote out. And once I have that, well, it's thumbs this direction. Counterclockwise is the direction of the current. So this way will be I induced, which is counterclockwise, number 2. Okay? Aren't these fun? These are some of my favorites of the entire semester. Are they fun because why are they fun? Oh, yeah. Let's see if we can make that change. Yes, question. In this particular right-hand rule, thumb is the direction of the magnetic field in the center of the loop, and fingers are the direction of the current around the loop. In this case, because the induced magnetic field is this way, my fingers tell me current goes counterclockwise. That goes back to the fact that it's trying to oppose the change. There's magnetic field that's pointing this way and growing, so the loop creates a magnetic field the opposite way to try to cancel out the growth. What's going this way? Yeah, the loop is moving this way, but in the directions, it says the magnetic field is growing. So here the loop's motion is irrelevant because that doesn't affect anything here. Let's see. I'm going to leave, which one do I want to do? Hold on. It's going to be okay. Yeah, I want to go to this one. I know, we're skipping a few, but we'll come back to them on Wednesday. It'll be fine. I'm trying to get to something before the end of the day. This will require 3 steps to try to sort it out. The square is the loop. Mm-hmm. Yeah?
Can we say like when like an area is going, if the magnetic field is increasing, it's always going to have a counter, and when it's decreasing, it'll go with. Like when we need to like be worried about like where.
I hesitate to make specific rules about that.
But how would you know like when it's going to have a counter versus like?
It's all about countering the change. So if something's being taken away, you're going to have something in the same direction as what's being taken away to sort of reinforce it. But if something is being added, you need something to oppose it the opposite direction.
So if something added, it will oppose.
Yeah.
If it's being taken away, it will try to maintain.
Yes. Yeah.
So we don't need to worry about, because I was like, if you're taking it away, it would try to maintain it.
Mm-hmm.
A confusing situation of like.
I'm trying to think if there's something where what you're saying wouldn't be true. And I can't come up with anything off the top of my head, but
right? Like
There could be something. I'm not totally sure.
that one instance where it could be like you're taking it away, but instead of like trying to maintain it, like at time or something like that. I think the opposite. Like you're adding, but
I can't think of a case,
okay.
but I can't promise it doesn't exist.
Yeah.
I hesitate to go that far. Let's answer this one and wrap things up. Who's got answers? 1, 2, 3? You're not sure. What's the direction of the original magnetic field? So we have to start here with the last chapter stuff. Thumb in the direction of the current tells me the direction that the magnetic field wraps around that wire, which means that everywhere over here, we have a magnetic field that points into the screen. Oh, let's draw a bunch of these. And everywhere over here, it points out of the screen. Whee! There we go. Okay? So it's wrapping around like this. As the loop moves to the right, well, R is increasing, my distance from the wire that's creating the magnetic field, which means it's experiencing a weaker and weaker magnetic field. Agreed? Okay? So that means that, let's see, B induced has to be in which direction? Yeah. So we need to reinforce by creating B induced in that direction. Once I have that, we can point our thumb in the direction of B induced and find that the direction of the induced current is clockwise. How'd you like that one? Things got a little harder, right? What's that? Can B induced is into the screen, so I induced goes around clockwise. Okay? Got it? I'm going to let you all look at that for a second. I need to scroll forward in slides just to make sure we can talk about what I want to before we're out of time today. Okay, I see where we are. Now, your lab this week has a lot to do with this, but there's a little bit more, okay? So you're going to get to play with this a lot and actually see the currents happen, and hopefully you'll get a better feel for Lenz's law and how that works. If you go back to the last set of slides, there is this particular thing which you are not going to quantitatively have to do much with. I just want to point out something that can happen. Notice in this diagram on the top left, let's see, we have a loop that somehow has a current in it. We're ignoring the fact that this is probably connected to a battery or something down here somewhere. And so let's pretend like something like this. So this is actually a loop that has a current being created in it, not because of a change in magnetic flux, but because we're making it happen. You may have also learned, if you've watched the videos, that if there is current that's in a magnetic field, it's possible to get a force on that current. You remember that a little bit, perhaps, maybe? Okay. So it turns out, if you think about this, there is current at the bottom that's passing this direction, and current along this part that's going that direction, and then there's current here, and then current there, and current back like this. Okay? Based on what you may have learned at this point, or may not have, I'm not really sure at this point what you've learned. I have no idea. It turns out that you can point your fingers in the direction of the current, so starting with the left-hand side of this, and if you orient your hand such that your fingers now bend in the direction of the magnetic field, your thumb tells you the direction of the force, which they've drawn here. So in this diagram, the left side of this loop is feeling a force away from you. If I go to the right side, exactly the opposite is true. So the current is going down, the magnetic field is over this way, there's a force towards you, okay? And you see that's drawn there. If you do the same thing with the top and the bottom, like at the top, it's like, point my fingers in the direction of the current. Now turn my fingers in the direction of the field, like you get stuck. That's because there's no angle between the two, which is because there's no force on the top or on the bottom of this loop, all right? But just the fact that we have forces in the opposite direction on the two sides means that if I put the loop here in this magnetic field in this orientation, and then all of a sudden turn on the current, it feels forces that make it want to rotate because of torque, which was everybody's favorite thing last semester, right? Yeah, see, that's why we're not doing too much with this. So if I pretend there's an axis down the middle of this current loop in a magnetic field will experience torque because of these forces sort of a distance away from that axis of rotation. The amount of torque and exactly how you calculate that's all on the right. We're not going to worry about those equations. You don't have to worry about that in here. You might play with it a little bit in lab, but nothing too severe, okay? I want to tell you that because if we go back to the slides we're currently on and go forward a few, somewhere. We've got this thing. Let's go one slide further, though, specifically this one. And we've got a similar situation. Someone is creating a magnetic field. You can see there's a north pole of a magnet, which must have a south pole over there somewhere. And right next to that is a south pole, and there must be its own north pole somewhere, so that we've got this magnetic field between these poles that's basically uniform and constant. This is not terribly unlike what we had with a parallel plate capacitor, where we have a constant electric field in between. So we create this magnetic field, and notice we've got, once again, a loop of wire that we're going to pass a current in with these connections. Don't worry about these connections so much. Just understand we've got the exact same situation as before. If I put a current through this loop, and the loop is in a magnetic field, the forces on the two sides of the loop cause a torque and make the loop spin. All right? If I have a situation where I'm able to, say, make the current switch directions, something we're not going to deal with in this class known as alternating current, well, then it turns out I can get this to turn sort of halfway this way, and then by flipping the current, I can get it to cover the other 180 degrees, and then we can continue to keep that happening through this rotational torque, all right? If I can then connect that to something that I want to spin, like, say, I don't know, the wheels on a car, all of a sudden we've just created an electric car. It really is this simple as well. This is the basic idea of an electric motor. A constant electric field, a loop of wire that rotates because I put current through it, all right? That's the electric motor. You'll play with that in lab. Let me just quickly say that you can do this thing in reverse. If, on the other hand, I decide to spin the wheel myself, I can get current to come out of this apparatus that wasn't there before. Okay, and that's the idea of an electric generator. We'll talk about all that in more detail later on.
So let's do this example. We have a 100 turn, or that just means that n is equal to 100. Rectangular loop of length and height as given, and it sits in a region of uniform magnetic field of magnitude B is 23 millitesla. The wire has a certain resistance, and then it says that the magnetic field is going to start decreasing at this rate in millitesla per second. Millitesla per second. So let's see if we can find a few different things here. First of all, number one, let's see if we can find the initial magnetic flux. The initial magnetic flux. So remember, it is equal to B dot A. And that applies for every single loop of wire that's there. So I should write that as N times B dot A, because every one has flux that's passing through it. So that's going to be N B A cosine theta. But in this particular case, theta is 0 because the magnetic field and the area vector, which would be out of the screen, are in the same direction. So that's just going to be 1. So I have 100 times 0.023 times the area, which will be 0.15 times 0.062. So we can find this initial magnetic flux, and I've got that number here somewhere. It's 0.021 Tesla times meter squared. And again, it's magnetic field times area, so Tesla meter squared. So that's the initial magnetic flux. We can, let's see, also find the induced voltage. We can find the induced voltage using Faraday's law. So if I just want to find the magnitude of the induced voltage, then it's going to be N times the rate of change of magnetic flux, like so, which we could rewrite as N times delta, and we already know this is going to be NBA because cosine of theta is going to give me 1 over delta t. The number of loops and the area are not changing, so I can take those out of the delta. So I have N, whoops, wait a minute, I got too many N's. I did N twice there, my apologies. We already included the N on the outside. This is just B times A. So let's see, the area is not changing. So I have N times A delta B delta T. And this delta B delta T is the rate of change of the magnetic field, which they gave us there. So this is going to be equal to 100 times 0.15 times 0.062 times the rate of change of the magnetic field. So in millitesla, need to be a little bit careful with that. That's going to be 0.00027 millitesla per second. So that's going to give me an induced voltage of, let's see, 2.5 times 10 to the minus 4 volts, from which we can find the current. So we could just say that the induced voltage is equal to I over R. So I induced is the induced voltage over R, so that's 2.5 times 10 to the minus 4. And they said the resistance was 12 ohms, so that gives me 2.1 times 10 to the minus 5th amps. So what direction is this current? What direction is this current? So again, it's decreasing. I have magnetic field that's pointing toward us, and it's decreasing, which means it's going away. So I need more of it. So that means magnetic field induced, is going to point in the same direction, be induced, which from the right-hand rule tells me that I induced is going to flow around counterclockwise. So it's in the counterclockwise direction, okay? So there is an example. Let's see. Induced EMF in a moving conductor. So I'm not going to say too much about this. I just want you to see how it's true. First of all, we could write an equation for this in case you need it. It's equal to B times V times L. And it turns out this is just the velocity of the conductor, and this is the length of the conductor. Okay, and notice we're illustrating this two different ways over in the diagram to the right. So in this case, we have a conductor, that's the conductor that's moving to the right, and we've got it connected by a loop of wire. So you can see the length of the conductor here, and its velocity is to the right. It's sitting in a magnetic field that's pointing at you. So if it turns out the conductor is moving to the right, that means more of this magnetic field is getting through that particular loop. If more of that magnetic field is getting through the loop, it's going to oppose that and give me an induced magnetic field in the opposite direction. An induced magnetic field in the opposite direction gives me current that flows around this loop in the clockwise direction. So I induced is this way. The thing is, it works out that I don't really need the loop of wire. I could just have a conductor itself, just a bar that's moving through a magnetic field, and you're going to get the exact same thing happen because of the force on the free electrons that are inside that particular conductor. So let's see. You can imagine that I have charges, positive charges are in here, and they're moving to the right. And remember, we can find the force on a point charge. So it's Q times V cross B. So V is that direction and B is towards you, which means on a positive charge, the force would be down. So the force is up on an electron. Notice, if that means that electrons separate and move here, there's going to be a dearth of electrons on the other side. That means I get a potential difference from one side of this conductor to the other. That's an induced potential difference. If you're wondering why any of this matters, what if that's an airplane wing? Ooh, an airplane wing is a conductor that's flying through the Earth's magnetic field, which would cause a potential difference to arise from one side of the airplane wing to another. It turns out there may be an example on this in your book. I actually have one that's here. Using some typical numbers for an airplane wing, it's something on the order of 1 volt. But it does happen, and it's something that has to be considered when we have conductors that are moving through an electric field. Okay? So let's see. We basically just did that example, so we don't need to talk about that. So what are some applications? Basically, we're going to wrap up this chapter by just giving you some applications of changing magnetic flux. So first of all, the electric generator. The electric generator is something that actually generates electric current. And if you've been thinking about what we've been doing, we've been creating a current that seemingly comes from nowhere. It just comes from the fact that magnetic flux is changing through a loop of wire. So if I were to take a permanent couple of magnets so that I can create a magnetic field between a north and a south pole, these two magnets, and then just put a loop of wire that's got that magnetic field passing through, and then turn that loop of wire, well, as long as this is turning, the amount of magnetic flux is always changing. And if it's always changing, it's always generating current. The thing is, in this particular case, because this is going to flip and then be the other direction, that means these two wires are changing, so these two are changing. What you're going to get is current that's induced one way and then current that's induced another way, and it's going to have a magnitude that's changing as well. This is how we generate an alternating voltage or alternating current, which we'll talk a little bit more about in the next chapter. So we put in the input ourselves. We do some mechanical work to turn the loop of wire through a magnetic field, and that mechanical work is essentially converted into electrical energy. The thing is that this works exactly backwards as well. What if I take current that's alternating, right? If I take the current and I'm always changing the current that's in here and I put it in a magnetic field, remember we said that if I have current that's going through a wire in a magnetic field, well, then that wire feels a force. And you can see that if it's a loop of wire, we briefly mentioned last time that would cause a torque. Well, this is just the reverse effect, and I'm going to get mechanical work. I can put in electrical energy that's alternating, and I'm going to get out mechanical energy by making something turn. This is essentially the motor for an electric car, if you want to think about it that way. It's an electric motor in general, but this is essentially how an electric car works. Take energy from the batteries and use it to turn the wheels, right? Transformers are another application, and we're not going to do anything with the calculations of this. Let me just point out that this is an electrical device which converts between different voltages. And it turns out, if you take a look at this diagram, notice I'm going to put in some electrical energy. But specifically, I'm going to put this in the form of alternating current, which means that the magnetic field that's being created by this coil of wire is like always in flux. Flux is always changing. If I put that near another coil of wire that has a different number of loops, well, then the amount of magnetic field that's passing through this coil of wire coming from this one is always changing. If the flux is changing, it produces a current. Ignore, if you want to, this iron core. This is all insulating. This coil is not physically connected to this so that there's no way for current to flow. It's just the fact that they're in proximity and the magnetic field of this one is passing through this one and changing. But the fact that I have a different number of loops means that in my N, the N in the equation, whatever voltage I have here, we're going to have a lower voltage over here because there's a different number of loops. And this works the other way as well. I could put my alternating current into this one and make whatever voltage I have here be higher over here because there's more loops. If you're wondering where something like this is used, just look at your cell phone charger. It has that little brick that's connected to it. It has a transformer in it. It's because the voltage that's coming out of the wall is too much for your cell phone or for your smartphone, so it has to be stepped down in voltage. There's a transformer in that little box that makes it, we'll say, a palatable voltage for your mobile device and gives you a voltage that's appropriate for that particular device. So that's transformers. This is also how electric power is transmitted. Generally, it transmits better with fewer losses if you transmit it from where it's created, well, or not created, where it's generated, to another place by using it at a high voltage. So typically you have those big transformers out on the power lines and like at the power substation and power plant that goes up to a really high voltage. And then when it gets closer to houses, it goes through other transformers that steps it back down in voltage before it gets into your house. All right. Let's see. So we're not going to do this. Boy, you got to love that diagram. Look at those lines. Those are beautiful. Yeah, that's nice. All right. And we're not going to do this. And we're not going to do this. You don't have to worry about it. Let me point out that just in general, this whole concept works. It's not just that changing magnetic flux creates a voltage and a current, but anytime I have a voltage and a current, there's also an electric field there. So we could say that in general, it also creates an electric field. So let me just tell you what the general equation looks like so you'll recognize it later on. So we'll say general form of Faraday's law looks like this. E dot dl is equal to minus ddt, like so. So this side has to do with the loop that's enclosing the area where the magnetic flux is changing. This is my changing magnetic flux, and we end up with an electric field that gets produced. That's the general form of Faraday's law. I'm not going to expect you to do any calculations with that. Which brings us to the last slide, which has some other examples that are around us all the time that use Faraday's law of induction. First of all, there's this man that's doing some serious singing. He's singing into a microphone. The way the microphone actually takes sound and converts it into an electrical signal is through means of a coil of wire. So what happens is there is a cone that can sort of catch the sound waves, and this is really, really lightweight, so that the sound waves hit this and will vibrate this cone, which is attached to a coil of wire, and that whole thing is sliding back and forth on top of a permanent magnet. So when that happens, you can imagine exactly how much of this magnetic flux is passing through the coil of wire is rapidly changing in a way that matches the vibrations of the sound. And it turns out the tiny little bit of current that's produced in this coil of wire, that's not just a solid current, but it's a dynamic current. It's a dynamic current that matches in some way the sound can be sent to an amplifier and amplified and recorded or boosted and played out over speakers, etc., etc., etc. Similar sort of thing for an electric guitar. There is a little magnetized portion of the string that is sitting, well, near a coil of wire, and as this vibrates back and forth, it's not unlike what's happening here. The magnetic flux is changing through this coil of wire, which means you're going to get an electrical signal that's changing. This says magnetic tape recording, but if you want to just think of this as the magnetic strip like on a credit card, well, when you slide the credit card through, this is a magnet, and it's a certain, very specific magnetic field that's going to be applied and changing through a nearby coil of wire in the reader, which generates an electrical signal that's changing, and it can be amplified and decoded and read. All of these simply involve magnetic fields that are changing in the vicinity of a coil of wire, which means that the magnetic flux is changing through that coil of wire, and that generates an electrical current that's also dynamic and changing and can contain information.